Hello, today we are going to learn about equipotential surfaces. Any surface which has the same electrostatic potential at each point, that surface we call it as an equipotential surface. Suppose for a single charge Q, the potential due to a single charge V is equal to 1 by 4 pi epsilon naught charge Q divided by distance R. The potential V will be constant for constant value of R. First of all, let us see, to understand this, we need to draw an equipotential surface. This is a point charge, suppose, positive charge. We know that the electric field lines, they go away from the charge radially. Now at each point at the same distance, suppose say from here to here it is R, from here to here it is R, from charge up to this point it is R. That is, if we take equal distance in all the field lines, then you'll get one imaginary surface. This surface we call it as equipotential surface. In equipotential surface, if I take one charge and then move from one point to another point on the same surface, then the work done will be 0. That means since they are the same potential, there will not be any work done. That's why it's written here, potential at any point on the equipotential surface will be always represented as 1 by 4 pi epsilon naught Q by R, provided R is fixed. At this point the potential, at this point the potential, at this point the potential, everywhere it will remain the same. Now again you can take the distance, suppose here up to this point it is 2R, like that here also up to 2R, 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 2R. If I take and draw one sphere, it is three-dimensional, we have to take it as a sphere. So this is another equipotential surface, but here distance is 2R. Now at each point the potential will remain the same. In that case, potential V will be same if the distance is 2R. But for the first case, if the distance from the charge is R, then it will be Q divided by R. So this is for a single charge. This is called your equipotential surface. Now let us see the relationship between electric field and electric potential. To know this relation, let us consider an equipotential surface. Suppose these are the equipotential surfaces due to a point charge. These are spherical surfaces. First of all, let us take a small test charge, a unit positive test charge that is being pushed by the electrostatic field from one equipotential surface to another along this direction. That is, let us take it as x-axis. Suppose this test charge is pushed by the positive source charge in this direction through a small distance dx. This from this position to this position. The electric field line direction, let us take it this way, making an angle theta with x-axis. The electric field line is coming from the source charge from here. It is going this way, and that way we can take it. Now we'll have to assume like this. Suppose a test charge plus Q naught one equipotential surface to another means the adjacent one, not the third one, but from first to the second equipotential surface to another adjacent equipotential surface. To a small distance say dx. Now this work done is not by the external force, but due to the presence of this source charge, it will be pushing. So negative work is done. So work done, we can write it as the work done by the electric field on the test charge is, you can write it as minus Q naught dV. As we have explained earlier, as I have explained to you, V is equal to work done per unit test charge. But this work done, if it is electrical work done, will be negative. So ultimately W is equal to minus Q naught into V. And here this potential we are taking in small quantity because the work done is also small. Only for moving from one point to another point to a small distance dx. Then this work done can also be expressed as the dot product of force and displacement. If you use your mechanics formula for work done, or this can be written as F dx cos theta, or this can be written as force is equal to Q naught to electric field intensity, then dx cos theta. F can be replaced with Q naught into E. These two work done, if you equate it, then you will get the relationship between electric field and electric potential. Let us equate these two work done expressions. Here, equating the two expressions, of work done, we can get like this: minus Q naught dV is equal to Q naught E dx cos theta. The E cos theta will be equal to this Q naught, you can cancel it out, minus dV dx, you will get it like this. This E cos theta is one of the component of the electric field intensity E along x direction. Downside, if you happen to draw a perpendicular here, this is base, this is hypotenuse. This is base, that is E cos theta. If you resolve it, this one can be written as E along S is equal to minus dV dx. So electric field intensity, here S I am using, actually it should be X along X axis, this along X axis. Now from here what you can understand is, if the electric field intensity is making an angle of 0 degree like this overlapping, then this cos theta, cos 0 degree is equal to 1, so become 1, and you get the expression for electric field intensity in general. This can be written as E, the electric field intensity, is equal to negative gradient of potential. Position we write it as R. So this is to be remembered, or we can write E is equal to minus potential gradient. This dVdr is also known as potential gradient. In the next coming topics, we will be using this as E is equal to V by R. In most of the derivations we will be using this one. Here we are doing in terms of small quantities, so we are doing dV dr in differential form. But later on we will be using in this way. So this is the relationship between electric field E and electric potential V. Electric potential V. The next topic we will be discussing is about electrostatic potential energy of a system of 2-point charges. Suppose you have 2-point charges. Here, before starting, let me tell you one thing. Electric potential energy for a single charge does not exist. So sometimes you may be thinking like, why not doing for a single charge? Electrostatic potential energy for a single charge is always 0. So you come to know while doing this why we require 2-point charges. Suppose there are 2-point charges Q1 and Q2. They are at infinity. In this case, you will have to build a system. Now, while building a system, you can just build it here itself. But for convenience, that system, let us take like this. A coordinate system, let us take, suppose this is x-axis, this is y-axis, and this is z-axis. This is the origin. Then it will become a little bit easier. We are going to do it in xy plane. I am going to build a system here. System, in what way I am going to develop is, I will bring those charges from infinity. These two charges are present at infinity. I am going to bring one by one into the system. Now the first one, to bring this unit positive charge Q1 from infinity to one point, suppose say here, let us take the position vector as R1. I am going to bring here. The amount of work done, in bringing plus Q1 from infinity to point, let us say A. Here at point A I have brought, will be given by, let me W1, it will be 0. Why it will be 0? Because work done is potential into charge. Potential into charge. Well, when there was no charge here, when you are bringing this charge from infinity to this point, it was empty. So charge is 0. So charge Q1 you brought and potential was not there. Potential was not there initially. So this value was 0. So ultimately the work done will be 0 when there is no other charge in the vicinity near the xy plane. But after this charge Q1 has come here, this charge Q1 will develop potential in the xy plane, and the potential produced by Q1, let us write it as V1. It will be 1 by 4 pi epsilon naught Q1 divided by distance where you are going to bring the second charge. Suppose here I am going to bring the second charge at point B. So this distance, let us take it as RAB. Let me take it as RAB. Now this potential that is developed in the XY plane, when you bring this charge Q2 at point B, suppose now I am bringing the work done in bringing class Q2 from infinity to point B is, I'll write this W2, it is equal to the potential that is developed by charge Q1 is this one V1 into charge that you have brought is Q2. So ultimately it will become V1. V1 is 1 by 4 pi epsilon naught Q1 divided by distance RAB suppose, and next charge is Q2. That is, you can find out the work done in bringing the second charge at point B. Let us say that this position vector is R2 from the origin. Now the total work done in bringing the charges from infinity, both the charges from infinity, will be the sum total of W1 plus W2. The total work done in bringing the charge or charges from infinity to that system. That system means these are systems that we have developed or we have built. To that system is W is equal to W1 plus W2. W1 you got 0, the work done bringing the unit charge Q1, and W2 is here 1 by 4 pi epsilon naught Q1 Q2 divided by distance RAB, distance between the two charges. So ultimately you get like this, the work done W is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by RAB. This gives us the expression for work done, and this work done is a measure of electrostatic potential energy, because we brought the charges. When we brought the charges from one position, from infinity to this position, we have done some work. This also, while bringing, we have done some work. Now, but when we look carefully, while bringing Q1, we have not done that much work. We can say that we are following Newton's first law of motion, because there was no charge nearby. So it was very easy for us. A body in motion will be in motion. So very little force only you have applied to bring the charge from infinity to position A. So the amount of work done is very, very negligible. That's why we are taking it as 0. We write here as 0. But when we talk about two charges that we brought, it means most maximum work you have done. Here you can see the expression, work is done in bringing the second charge. This work that we have done to bring the charge from infinity to this point gives us the measurement of electrostatic potential energy of a system of 2-point charges. So this work done is stored in the system as potential energy. Therefore, potential energy we represent with U, that is equal to W 1 by 4 pi epsilon naught Q1 Q2 divided by distance, that is from A to B. This gives us the expression for work done for a system of two charges. Now let us see for a system of charges, or say 3-point charges. The next topic we'll see electrostatic potential energy of a system of 3-point charges. Then what we have to do? Suppose there is one more charge at infinity. All these are positive charges, say plus Q3. Now like that, how we proceeded before, we'll do in the same pattern. First we'll bring Q1. To make our diagram easy, we'll not take these position vectors. We'll take the coordinate. This way we'll take it. Suppose we brought this Q1 here first. Then what is the work done? Then the work done W1 will write this equal to 0. So no work is done. But potential is set up by the charge Q1. So V1 will be how much? Then we'll write 1 by 4 pi epsilon naught Q1 divided by distance. Now whose distance? Suppose this is A. Now Q2 I am going to bring. Suppose this is Q2. This point is B. Then I will write RAB. Or I can write 1, 2. R1, 2. This is the potential set up by A. Now when you bring charge Q2 from infinity to this point, then the work done, let us say it is W2. Then it will be V1 into charge, what you have brought. Then potential V1 is 1 by 4 pi epsilon naught Q1 R12 into Q2. This is the work done while bringing the second charge. Now let us say the third charge we are bringing, let us take it here as point C, Q3 I brought it. But this time when I am bringing Q3, before bringing you should be sure that this Q1 is also having potential, Q2 also has developed potential. Now two potentials are there. So the potential V2 or V3 let it be for the third charge we are going to do, or we can write V1 plus V2, that will be better. V1 is for the first charge developing the potential, that will be already is there, 1 by 4 pi epsilon naught Q1 divided by, for this charge, let this distance, this one we are taking it as R12. Then here let us take the distance as R13. And here let us take the distance as R23. Then we can write the distance is R13 for the third charge, plus 1 by 4 pi epsilon naught. This is due to the second charge, potential developed by the second charge, that is Q2 divided by distance is R23. So if you take 1 by 4 pi epsilon naught common, you will get here like this, Q1 R13 plus Q2 R23. This will be the potential developed by the first and the second charge at this point C. Now when you bring the third charge, the work done W3, the third work done will be the potential V1 plus V2 into charge Q3. So ultimately this V1 plus V2, potential developed by Q1 and Q2, that is V1 and V2, their sum total this one, multiplied by this Q3, then we get the third work done. So I am writing here work done W3 is equal to V1 plus V2 is 1 by 4 pi epsilon naught Q1 divided by R13 plus Q2 divided by R23. You are multiplying with simply Q3. So ultimately it will become 1 by 4 pi epsilon naught Q1 Q3 divided by R13 plus Q2 Q3 divided by R23. Like this you can find out the third work done by the third charge. After you find out the work done by the third when bringing the third charge from infinity to this point C, the net work done by the system of 3 points, that is 0, the second work done, and then the third work done. We have to add it up. So the work done in bringing the charges from infinity, all the three charges will be the net of sum of W1 plus W2 plus W3. So now W1 is 0 plus W2, you can see I have wiped off. It should be 1 by 4 pi epsilon naught charge Q1 Q2 divided by distance R12 plus this one 1 by 4 pi epsilon naught and require a larger space, so I have to wrap the diagram. It will be Q1 Q3 divided by R13 plus Q2 Q3 divided by R23. So now this is 0, leave it aside. These two you can take common. 1 by 4 pi epsilon naught Q1 Q2 divided by R12 plus Q1 Q3 divided by R13 plus Q2 Q3 divided by R23. So this will give us the net work done by the system of three charges. So it's very simple to remember: 1 2, 2 3 and 1 3. And whenever you do 1 2, distance will be from 1 to 2. Charge 1 and 3, distance will be from 1 to 3. And charge 2 3, distance will be from 2 to 3. So let us do a numerical based on this formula and see. Let us solve this question and see. If one of the two electrons of hydrogen molecule is removed, we get a hydrogen molecular ion, that is H2 positive hydrogen ion. In the ground state of an hydrogen positive ion, the two protons are separated roughly by 1.5 angstrom unit. So let us draw the diagram. These are the two hydrogen ions. Two protons. Let us take PP as proton. They are roughly separated by around 1.5 angstrom unit. And the electron is roughly 1 angstrom unit from each proton. Let us take the electron here. It is separated by 1 angstrom unit. This is also separated by 1 angstrom unit. This is a 3-charge system. Protons are positively charged, we know, and electron is negatively charged. Determine the potential energy of the system. Now we are going to find out the potential energy of the system. We'll use the earlier formula, but here some distances, they are given in angstrom unit. You need to know 1 angstrom unit is equal to 10 to the power minus 10 meter. 10 to the power minus 10 meter. So distance between proton and electron, let us do a solution like this. Distance between proton and electron. To make it easier, let us take it as proton electron. Here you have one R1 let it be R2, let it be R3. Let us write this R1 equal to 1 angstrom unit, that is 10 to the power minus 10 meter. The distance between the R1 and R2 both are equal. R1 is equal, that is equal to R2 also. And then the distance between proton and proton, or two proton, distance between two protons also you can write, let it be R3, this 1.5 angstrom unit. So you can write this 1.5 into 10 to the power minus 10 meter. And charge of proton, you already know it is 1.6 into 10 to the power minus 19 coulomb. This positive, protons are positively charged. And charge of electron, one electron is equal to minus 1.6 into 10 to the power minus 19 coulomb. So now, if you write this proton as Q1, Q2, Q3, that way also you can do, or you can do PP, charges are plus P, whichever way you like. Suppose this one is Q1, this is Q2, and this is Q3. Q1, Q2, Q3 you can write down. Then potential energy Q is equal to 1 by 4 pi epsilon naught Q1, Q2. Now Q1 and Q2, distance is how much? Between Q1 and Q2 it is R3. So I am writing here R3 plus Q2 and Q3, which is Q2. This is Q2, this is Q3. Distance is R2 plus Q1 and Q3. Q1 and Q3. What is the distance? Then we say R1. So like this, write down. Then put the values, whatever values you have, and then we have to calculate. Now let us put the value and then see. So U is equal to 1 by 4 pi epsilon naught. The value is 9 into 10 to the power 9. Then you have Q1 and Q2, both are positive. 1.6 into 10 to the power minus 19 square will come, divided by R3. R3 distance is 1.5 into 10 to the power minus 10 meter, plus Q2 and Q3. One is minus and one is plus. It look like this: 1.6 into 10 to the power minus 19 into minus 1.6. Minus into plus will give you minus, so ultimately this will change it into minus. So instead of writing twice, we will be writing whole square, divided by R2 is 1 angstrom unit, is 1 10 to the power minus 10 meter, plus, again this plus also will change to minus because R3 is minus, so it will be 1.6 into 10 to the power minus 19 whole square, divided by 1 into 10 to the power minus 10. Then we will take out the common terms outside. That is 9 into 10 to the power 9. You have 1.6 into 1.6 into 10 to the power minus 38. Minus 19 into 2 is 38. There is common term everywhere. Downside you have 10 to the power minus 10. That is common. Then in the bracket you have 1 by 1.5 left out here. Here everything taken out. Only this is left out. Minus everything taken out 1. Here also everything taken out 1. So here what we'll get is 1.6 into 1.6. 6 6 are 36. 6 1 6 7 8 9. 6 1 6 15 5 1 and 2. Decimal is after 2 digit. Again multiply by 9. 9 6 are 54. 9 5 are 45. plus 5 is 50, 0, 5 in hand, 9 is 18, 19, 23. After decimal we have 2 digits, so it is 23.04 into 10 to the power 9 minus 38 is minus 29. Then minus 10, if you take it up, will be plus 10. And inside the bracket you can make this as 10 by 15. And minus 2, minus 1 is minus 2. 5 3 times, 5 2 are 10. This will become 23.04 into 10 to the power minus 19. Minus 10 plus 10 is minus 19. And then this bracket term, if you take LCM, 2 by 3 minus 2, it will be 2 minus 6 by 3, it is minus 4 by 3. Minus 4 by 3. Now multiply it. If you can cancel, 3 7s are 21, 3 6 are 18, 3 8 are 24, can cancel, 3 6 are 18, 3 6 are 18, 3 7s are 21, we can take 7, 7s are 21, 2 0, 3 6 are 18, and then 2 4 3 are 24. After decimal 2 digit you have, then multiply it. 7.68 into minus 4, 32, 24, 27, 2 in hand, 22 and 30, 30.72 minus 30.72 into 10 to the power minus 19. You will be writing the SI unit of energy, that is joule. Now the next thing is the last part of the question. Potential energy at infinity is 0. They are asking us to specify. So in which case potential energy will be 0. Under what condition potential energy will be 0? Then we write down potential energy at infinity is 0. At infinity always potential energy will be 0. Thank you.